we have the privilege of listening to our international speaker, Robin Power. So as he comes up, he's going to speak to us on the subject of unlocking the secrets behind modern integrated compaction testing. He is the CE of Insitu Tech, and he brings a fresh way of thinking, combining experience, knowledge, and business acumen. He also has more than 15 years experience in working across Australia, New Zealand, and the Pacific, and I understand he's from Tassie. So welcome, Robin.
One secret's out of the bag already. I wasn't expecting that. Thanks, Giannis. All right, so let's move on. So I want to start by just getting some fundamentals out of the way. So the compaction process. Is this a pointer? Sort of, yep. All right, so in terms of the compaction process, the objective is to, we have got our mineral particles, we've got voids, so air gaps essentially between the mineral particles, we've got some moisture in there. Hopefully we've got no organic matter. And the objective of the compaction process essentially is to reduce the air voids and then also to create better interlocking between the particles. That's the objective. And it doesn't matter whether it's bulk earthworks or foundations, backfills, which we've just been talking about, or pavements, it's the same. And for compaction, for a lot of soils that we work with, moisture plays a really important role as well. So whatever I'm going to talk about, moisture still plays a role. Okay, so let's not fool ourselves, kid ourselves. So compaction is really important for a couple of reasons. One is for resilience of whatever we're constructing, and the next is longevity. And so what I want to introduce you to is some thoughts, ideas, which I'm kind of like drawing together different threads that I've been hearing in this conference as well. The first is about creating a uniform. So having uniformity in compaction is kind of like a holy grail. And also quantified compaction process. And then secondly, to deliver that as efficiently as possible. And so what I'm talking about is the combination of instruments on the rollers and real-time feedback together with in-situ testing, which essentially enables us to have an integrated compaction control approach. So what this enables us potentially to do is to compact deeper in-situ material than we would have been able to compact previously, and also to compact deeper lift thicknesses than we have been able to achieve previously. And if from an outcomes perspective, this is helping us from the point of view of improvements in productivity, reduction in cost, quality improvements, going to be very attractive as far as the end client's concerned, and depends on how you're rewarded as well as far from the contractor perspective, reduction in risk, and also as a side benefit, reducing your environmental impact. All right, so compaction. How do we typically assess compaction currently? Talk to me. How do we do it?
Probably through nuclear testing.
Nuclear density testing, yep, that's one of the methods.
Clegs.
Clegs, yes. Anything else? Any others come to mind? NDMs, yes. Said already, yes. Scalar, yeah. Those are typically the methods that we're going to be utilizing. Now, all of these methods are essentially enabling us, the objective is really to enable us to assess density. Now, density, if we think of it from a pavements perspective, this conference is all about roading, density from a pavements perspective is not actually what we're interested in. What we're interested in really is stiffness. Stiffness, when we design pavements, we typically design using stiffness or a modulus. And so what we want to do is we actually want to be able to assess modulus in situ. So I wanted to chat to you a little bit about density and real-time feedback and so on, but I don't have time to do that. And so forgive me while I just jump over these slides. I'm not quite sure why they're here, but just give me seconds. Okay. What I want to do is just to share with you a fundamental change that we've seen happening. So this change started in Europe in the 90s. In the early 2000s, it became prevalent in the US, and we've seen this both here in New Zealand and in Australia on a project-by-project basis being implemented. And this change is a move from density assessment to stiffness assessment. And again, stiffness being much more reflective of the dynamic loadings, the traffic loads that a pavement will undergo. And just to be also very clear as well, there are fundamental differences between stiffness and density. We're actually trying to achieve different things. And from an outcomes perspective, sometimes when we measure density and stiffness and relate them, we'll have one going up and the other going down. Okay? And so there's a fundamental disconnect here in the way in which we typically carry out our compaction assessment process. So what I want to do is I want to introduce you to some of the more current innovative processes. And first of all, what we're going to do is to talk to you about the in situ measurement process. So what we've seen is we moved away from scalas and NDMs towards using other tools like lightweight deflectometer and plate load testing. Has anybody got experience with plate load testing? Quick show of hands. One, okay. Two, what about lightweight deflectometers? No. Yes, one, right, okay, excellent, thank you. Yes, no, these are different things. The Benkelman beam is a different test. Yeah. So I know that the Benkelman beam is used here. One of the things about the methods that I'm going to introduce you to is these are methods that remove any ambiguity in the testing process, kind of like agnostic from the operator. It's not reliant on the skill and expertise of the operator. So that's something which is pretty important. So plate load testing. So this is a base test, if you like. This is the probably the most sophisticated setup that you will find in the marketplace. Essentially, we've got a counterweight, like a roller or an excavator or something like that. We're jacking against it. We're pushing a plate into the ground, and we're doing that in increments, and we're measuring deflection. And essentially, the idea is that we come up with a graph, which we do two loadings. We load, unload, and reload. And this gives us an indication of the modulus. So EV1, EV2, if that's familiar terminology to you, and the ratio between these. Now, great test, regarded as a gold standard, but we need a counterweight, and relatively speaking, it's slow. Even with the best tech, you're talking between 20 and 30 minutes per test. So what the Germans did in their wisdom was they went, we've got these really quite defined, much smaller range of capability of a plate load test. We would love to take that capability, but make it a lot faster. And so they came up with a tool called the lightweight deflectometer. So this is a layer-by-layer compaction control tool designed specifically to enable us to get real-time feedback of how we are progressing with a stiffness-based assessment. So we're measuring deflection and then calculating stiffness from that. And we can relate it back to our resilient modulus through plate load testing as well. It's fast, 3 minutes per test. And we've also got high levels of repeatability as well. So that's important. And we can also get an indication of the level of compaction of the material. We can also work with larger grain size material as well. So NDM's typically limited to anybody who's NDM specialist, about 20 mil. Okay, that's the largest type of grain size that you can work with. So what do you do above that? Do you just not test? So you can use a tool like the lightweight deflectometer for grain size, something like 60 to 65 mil. It's not impacted by backscatter in trenches. So we can use it for trench work, contaminated sites. I'm just giving you some like starter examples of how people start to use this. We're seeing lightweight deflectometers being used on major infrastructure projects here in New Zealand by companies like Downer, Fulton Hogan, companies like that. They're using a self-control device because it enables them to test and get an instant understanding of the in-situ conditions and then be able to move forward to the next phase of assessment. So you might ask the question, how do we... So we have a specification. It's a density-based specification. We don't have any influence over that, the creation of that specification. Typically when a client comes to us and they say, we want to use the lightweight deflectometer and we've got a density-based specification, we go back to them and we say, can you have a conversation with your designer about specifying a method which aligns with the design intent, which is typically modulus-based. In some cases, they don't have that luxury, and so there is a technical note which has been created. This is part of the ARRB, is now the National Transport Research Organisation. This technical note is basically a how-to guide of how to take a density specification and then translate that into using the lightweight deflectometer as a in-situ testing method. So it has charts in it like this, which is essentially a how-to guide. So for example, is my material sensitive to moisture? Yes, take this path. If it's not sensitive to moisture, then take this other path. So if you want to grab that link, once again, it's a really valuable standard. Okay. So one other way that you may be familiar with, FWD. Who's familiar with FWD? Lots of hands go up. Okay, so FWD is great, but it's about having access to that capability. So availability of having access to a tool like this, and it's typically used for stiffer pavements, so it may be used on base layers. You can use it on subgrade, for example, but typically it's used on base layers or on top of the asphalt as well, or on top of chip seal. And these are layers which are more difficult to test with a lightweight deflectometer because you don't generate enough pressure and deflection on the pavement to get meaningful information. So each method has its role to play. All right. I want to link these things together. So I'm going to introduce you to intelligent compaction. Has anybody got any familiarity with intelligent compaction? Okay, 1, 2 hands. Okay. Sort of. Yes, right, okay. Somebody saw a little presentation earlier. Essentially what we're trying to do is to connect the in-situ testing methods with the rollers. So at its most basic, what we're talking about is instrumentation mounted on the rollers, and we've got feedback for the operators, so real-time feedback for the operators, and then we've also got the potential to do real-time monitoring. Imagine you have got 2 rollers, they're connected together. The data is being synced between the roller operators every 15 seconds. and also somebody who's working remotely, for example, a supervisor, right? So they can see what's going on site as well. So for the roller operators, they are pretty much always having the same view. So they know their progress towards an objective, an outcome. And that's very attractive. So this can be used both for asphalt and also for soils as well. And this technology, in some instances, it's included from an original equipment manufacturing perspective, so for example, Bomeg down the back there, or it's retrofit. So we're in the retrofit space. So here's an example, and what I'm going to talk to you about to start with is pass count monitoring, okay? Very simple. It's a low-hanging fruit. So if you're going to start anywhere, I would suggest you start with pass count monitoring. So this is essentially instrumentation which is mounted on the rollers, which enable us and the operator to see where they've gone, where they haven't gone. So here we've got an example. So before, at the top, was rollers fully instrumented. The screen is covered up. The roller operator is experienced, knows exactly what they're doing, worked in the industry for a long period of time, trying to do their best work. Before is what you see. The objective was to deliver 3 passes. That's blue. Look at before. You'll see there's a little bit of blue. Lots of light blue and green. There's also some yellow and some red. Red means 1 pass. Yellow means 2. Now we take the cover off the screen. Roller operators never used the tech before. And this is what they delivered, the after picture. So for using the tech inexperienced perspective, you can see how valuable that is. Imagine that was your pavement. So I'm going to, let's see if this works. So now we've got one roller, and this is the roller path. So this is what we call a playback video, but imagine this is what the roller operator sees on the screen. So then we've got a second roller jumping in, and so on. So you can imagine like how that process works. And that playback process, by the way, that's a really valuable tool from helping the operators to review how the shift went, right? So just like that, we reviewed, I don't know how long that would have taken to do, but those who've worked in a roller operating environment will have an idea of how long that would take. So here's a real world example. This is happens to be, I'm showing you publicly available data, okay? So it's difficult to get this publicly available data, so NTRO has done a piece of work here, and this happened to be a road junction project. It was asphalting. It was done at night, okay? So quite challenging conditions to work with, even for experienced operators. What we were trying to deliver was 7 passes. That's blue. Anything that's purple and above is over-rolling. And if we look on the right-hand side, black is 17 passes and above. We'll just let that sink in. We're supposed to be delivering 7, and black is 17 passes and over. Okay? Now, what happens if you over-roll asphalt? Can it be detrimental? Some nodding heads. Absolutely. All right. So to conclude, from a pass count monitoring perspective, and by the way, we can also include temperature in the mix as well. So that's important. So from a pass count monitoring perspective, essentially what we're doing is to deliver improvements in terms of not over-rolling. In our experience, for example, from a soils perspective, typically that's around 30%. Also from a soils perspective, eliminating the need to bring in additional material because we've over-compacted, and let's say we needed to reach an RL here. We've used all our material, we only got to here because we've over-compacted it. No gaps, no under-rolling. We've delivered uniformity in terms of passes, okay? Fuel savings, et cetera, et cetera. So the next level of sophistication is a stiffness, an indication of stiffness. So this is helpful because it enables us to get an indication, and I use that word advisedly, of how stiff the material is. And so here's an example on the screen. Here's another one, so example of detecting soft spots. So when the material was dug out, we could actually stand on it and it would move. And this was picked up by the roller. So to wrap this up, the stiffness piece, so it helps us to identify those anomalies, soft spots, anomalies, for example, on the screen. This was a culvert which was underneath, which was undetected, and gives us 100% coverage. Now remember, with our traditional approach, we do one NDM over here, one NBMB over there, and that's supposed to be representative of the whole lot, okay? And the rest of it is based on the feel of the operator or them trying to remember how many passes they've done. And there's also the possibility of increasing lift thickness and using these technologies. So the last thing that I want to do is to introduce you to this concept of increasing lift thickness. Now this case study that I'm going to share with you this is from Queensland. They actually doubled the lift thickness. It's a very thorough, rigorous case study. It was done for a large construction project. What's interesting about it is that they actually placed material in lifts beyond what they believed that the rollers could achieve. So it was 300 mils, 600 mil, 800 mil, and a meter. And so they were looking to demonstrate two things. One is how deep the rollers could compact, and then secondly, how methods to be able to assess the stiffness of the material. Not density, but stiffness. But they wanted to compare that with the traditional density assessment processes, and that was done during this process. They took different thicknesses of material, also different materials were evaluated, and also field moisture, and also moisture-conditioned materials, and also different numbers of passes. And including in that heavier rollers, but with smooth drum, and then also with pad foots. So the outcome. From the client perspective was that they actually increased the lift thickness from a traditional 300 mil to 600 mil. Now, this is a main roads project, okay? So that was signed off by the client, their technical advisors, the contractor, their technical advisors, and the designers, okay? And one of the learnings is to have collaboration from the beginning. When you're looking to take an approach like this, do not introduce it partway through. Get it introduced right at the beginning. So one of the objectives and one of the designers' roles, or the people who put this concept together, was to make sure that there was no change in onus for the contractor, and also no loss of quality for the client. And those were really important criteria. This methodology was used for the bulk earthworks, granular materials, but not on the bound layers. And it was also used on load transfer platforms. This is some of the different methods that were assessed, and their different depths of footprint. So we've got the NDM on the left-hand side, also same sand replacement, about 300 mil, lightweight deflectometer, zone of influence about 450, plate load test about 600 mil, zone of influence can be deeper, and then another tool called the Panda, which I introduced right at the beginning, which is a penetration test. And what we saw was that one of the methods that was approved was a combination of lightweight deflectometer, fast surface-based modulus assessment, together with the Panda test, which is a strength versus depth profile, enables us to understand stiffness over depth. Now, importantly as well, to give the client confidence, on a monthly basis, they went back and they reevaluated where there are traditional approaches to make sure that their traditional methods were still being satisfied. Okay? but they were not running in parallel, the traditional method, and these more innovative methods. They basically choose one path, stick with that, and then periodically, on a monthly basis, do a validation to make sure that they're confident. Okay, lessons learned. I mentioned about the early collaborator, the early contractor involvement being really important, and also using consultants who've got that track history. That's what I wanted to share with you. There's now some time for questions.
Thank you, Robin. Any questions?
Yeah, interesting stuff. Just on your number of passes, probably a little bit, in terms of, where the number of passes actually achieves compaction. I mean, I like your stiffness test, that's good, but I just, maybe for asphalts and stuff, yes, but in pavements, I'd be a bit suspect about
So the way that the number of passes is come up with is you will do trials.
Yeah.
And the trials will basically validate your methodology as long as you have a relative uniformity of materials. If you're getting substantial changes in materials across the job, that doesn't work. But if you've got a project where you've got uniformity of material, that's going to be really helpful.
Okay, and then your deep lift, 600 mil, that's pretty
Yes.
impressive. So,
Yes.
And you were getting full through the whole layer.
That's correct, yes. Actually, what the results showed was that we were getting full compaction to 800 mil, but what they decided to do was to wind it back to 600 mil from a conservatism perspective, safety margin.
And just query, that was pad foots, was it?
Using pad foot, smooth drum, and the materials that were used were sandstone, siltstone, and also basalt.
And you didn't talk about vibration there.
Great point, thank you. For stiffness assessment, you must have vibration on the rollers, okay? And absolutely, vibration was used for that compaction. So thank you very much.
Okay, so then one more thing, sorry.
Yes.
Is over vibration is probably worse than over rolling. How do you manage that one?
Well, you can also assess the level of vibration, so that can be reported as well, and the roller operator can have that come up on the screen. So if that's a concern, or also, post-analysis, you can also see that as well. And the other thing is that you're developing a track history, right? So all of this data is stored, and you've got that as a record for, future review if necessary as well. There was a question over here.
Yeah, I just worked in Queensland for a while out in the outback,
Yes.
so I saw the Flinders Highway up there, and I think it's just probably important to note that we don't usually like sandstone and silty materials with clays in them. It makes for a fascinating test case because you're using these really wild materials, but they do respond. So, like you say, this is like a hardcore focus on the loading that would be, how it would affect a pavement because it's so unique in these situations. It's not, we're generally like a basalt type country, and it's just slightly less sensitive to those things.
Look, you're absolutely right.
Yeah.
So please don't be under any illusion that this can be achieved with whatever materials you've got available. This is material specific. So great point. What I wanted to do is I wanted to showcase a really rigorous piece of work which had been done to get across the idea that you can challenge that it can only be 300 mil lift thickness, for example. So thank you for that question. That was really valuable.
Any more questions? I'll go for the one on Slido. So are there currently any material testing methods that can be done to support design that gives material suitability for stiffness, or only use practice notes?
So what we're seeing is that these approaches are being written into specifications on a project-by-project basis. So there are standard methodologies for how do you carry out the test, for example, but it's on a project-by-project basis that it's being specified. And then, for example, in that technical note that I showed you, it again, like I said, it's a step-by-step process, and when you are specifying, you will come up with a very clear set of parameters about how the rolling process must be carried out, and then also how the testing process must also be carried out. So very clear, so there's no ambiguity. And also, for example, the time between when you compact and when you do the testing as well. So that's also covered.
Robin, are you aware of any New Zealand agencies or suppliers that's considering the use of this technology?
Actually, really interesting question. So I was in a session earlier, and the National Pavement Technical Group is actually looking to reassess the fundamentals which we use to assess the quality of a subgrade. So these techniques are being used here in New Zealand, and also so specified onto projects. But there is an intention to actually look at the real fundamentals, because, for example, we've got CBR, we've got California bearing ratio, we've got stiffness, we've got density. They are different measures, right? And then we're using like loose relationships like modulus is 10 times CBR. These types of things, they're like so loose. We can do better. We are doing better. Let's implement better on a broader basis. So if you're interested in that work, the National Technical Pavement Technical Group is looking at that right now. And I was excited to learn about that. So.
Any further questions? Well, thank you, Robin. That was really insightful.
Thank you very much.